This video, we're going to work through some exponential function problems. So on this very first one, we are given a function to model salary at a new job, and it's given right here. So it's an exponential function, which means it's percent growth. And we have, if we think back to our parts of our exponential function, and I'll just write that right up here at the top. So remember, we have this sort of general form where A right here, we like to call that our initial value. It's the value of our output at sort of whatever year we're tracking from. And then the second most important piece is this R value. It's the decimal form of our growth rate, which is a percentage. And so this is our growth rate. And typically it's an annual growth rate. And key is it's a decimal form. So we have to do a little bit of work to sort of write it as a percent like we prefer. All right, so knowing this, so we have this function that represents salary, and T is number of years since 2024. So if we're asked for our salary in 2024, that's just a fancy way of saying what is our initial value? And remember, our initial value is being multiplied by the base of our exponent. And so right here, that would be that $67,000. And so that would be the salary in 2024. Now, annual growth rate, that's this R that we're looking for as a percent, but I'm not given R. Instead, I have this whole 1 plus R. And so I can do a little bit of work. And remember, we talked about in class, some of us might be able to just look at the equation and pull out that R value. But just so that you get some practice, you could also set yourself up. Oops, I don't want my keyboard. Go away, keyboard. I could set myself up a little equation because that 1 plus R, that entire thing in parentheses, is what we did to get 1.032. I'm going to subtract 1 from both sides to solve for R. So R equals 0.032. Now be aware, this is not the growth rate yet. Our growth rate should always, always, always be written as a percent. So I need to take my answer and still times it by 100 to get that actual percentage rate. And so here, that would end up being 3.2%. So each year, your salary is going to go up 3.2%. Hopefully it matches inflation and that, you start making more money. And the next question, so what is your salary 7 years from now? Now, this is basically, we're just plugging in 7 into T. And so if in a calculator, we'd be evaluating 67,000, 1.032 to the 7th power. Now, I like to use Desmos for problems like this because it's just I can see and make sure the exponent's what I want it to be. Now, I did write it in as a function, and I can keep this, and I'm going to keep that there. But, this is really just asking us to type in 6700, but oops, without those extra decimals. I'm having some difficulty this afternoon. Sorry about that. And then that A to the B is my power button. And so, in 7 years from now, if you keep increasing at the same rate, you should start earning $83,528.12 per year. Now, approximately what year would you earn double your current salary? So there's a few options to do this. So one, I need to know what double my salary is. I like to think that. So times 2. So it's looking when you make $134,000. Now, one option is to sort of guess and check. Like I can start plugging in numbers, okay? When I get here and I get 10, I'm at 91. Ooh, that's not even close. So I'm going to take a bigger jump and I'm going to go to 20. Oh, 20 got me closer. Notice I'm almost at 134,000. So maybe I go 5 this time. Up, I passed it. So I'm going to come back down. So, now I might go a little slower. Okay, I'm still above it. Ooh, I'm getting pretty close. I'm only 4,000 extra. And then if I go here, notice I'm a little below. So I would say somewhere between 22 and 23 years. And that method you just saw me use would be guessing and checking. So that's method 1. Another way I could test would be called the rule of 70. And so the rule of 70 is, I like to say, math magic at its finest. Basically, if you take that growth rate we found in part B, and you go 70 divided by that growth rate as the percent, it gets you an approximation. So 70 divided by 3.2. And notice up, so 21.8 or 21.9, that's about 22 years. So that answer would also be acceptable. And then the third and final strategy is to use those TVM solvers we were actually learning about just recently in class. So if I open up my TVM solver, I would be solving for n. Remember, our I value is our growth rate. Our initial value is our PV is sort of our initial value. We want to know when we get 2 times my initial value. And the payments per year and compounding per year, we keep that 1, and we want to solve for n. Oops. And it's not, ooh, it's because I forgot to make one of these negative. Thank you. See, look at all these fun things you see when you get to watch me make videos. Okay, solve for n, 22 years. So all of our answers sort of agree. They're all sort of different strategies to dealing with this problem, and all are totally acceptable to use. You sort of find your way that makes the most sense to you, and know that you're saying we're approximating. So any of those would have been acceptable means to sort of figure it out. So with the TVM, we got 22 years. All right, our next exponential problem is using a graph, and then we're going to be doing some stuff with the graph. So we have this graph here, and it shows tequila mezcal sales by liter cases in millions, and the amount it's increased in the US. So we have in 2003, it was around actually, given the exact value right over here, 8.009 million. And then in 2022, we were already up to 29.868 million. And we are asked for our absolute change in tequila sales. So that, remember, it's new minus old. And so I'm going to go over here and just plug it into my trusty dusty calculator. Hopefully typing everything correctly. And I would get 21.859. Now, a few things, because this came up on our last test. Don't forget to label this. So 1, it's millions. So I do need to write millions afterwards. And then that with an absolute change, we always have to state, is it an increase or a decrease? So in this case, it's an increase. So the amount of sales increased by this many million. Now, the next question is asking us for the relative change. So the relative change takes our absolute change and then divides it by the original value to sort of get the sort of percent change in the growth over that time period. And then we want to write this always as a percent. So we're going to times it by 100. So what I like to do is I just go over to my calculator and I take the expression I already had and I divide it. And then I times it by 100. And then here's the neat thing. If you round this to the nearest percent, that would come out to 273% increase. And I want you to notice something. This is what I found really cool. Look right there. 273% increase, 273% increase. So that number on the graph right here, that was our relative change. Isn't that cool how they had the relative change on the graph? I thought that was really fun. So, you never know. Now, if we took that relative change and we broke it up by what was sort of the percent that it increased each year, we could create an exponential equation to sort of model this data. Now, the thing about models is they're never perfect. So the bar graph shows the actual values, while this equation right here is sort of a way to predict or approximate what we think is going to happen with our tequila sales. So what is the annual growth rate of sales according to my lovely exponential function? Remember, that's where we're going to look at that 1 plus r. And we want to figure out what r is. And so we'd end up with r equals 0.072, and we want to write that as a percent. So that would be a 7.2% increase each year. And what would we then predict the sales to be in 2024? So that's 2 years after the last date on the graph. But the easier thing to do is going to be, well, how many years since 2003 is 2024? So I'm going to just do a little quick subtraction over here. So I have 21 years later, and I'm going to plug 21 into my function. So I have 8.009, 1.072 to the 21st power, and it says about 34.5 million 9-liter cases would be sold in 21 years. Now, I'm curious whether or not this is like close or generally seems to be on par. So I picked a random date, and we're going to compare my equations value with the value that I'd get that is on the graph. So we're looking at 2015. And so a good trick here, you guys at home could take a ruler, but I don't have a ruler. So instead, I'm going to, and I'll do it in black. I'm going to use, oops, and shrink this a little, a handy dandy line. So I'm going to go here to the top. So we have 2015, that's right here. It's this bar. And I'm going to go to the top of that bar. I'm going to sort of, sketch a line. There's the top. There's where it is. And I'm looking and I'm saying, okay, that's pretty darn close to 15. So we're going to call that 15. And then I'm going to go over to my equation and I'm going to do exactly what I did on the second part of this question. So I basically need the difference. I need from 2015 to our initial year of 2003. And notice I just put that straight into my calculator. I'm having it do all the subtraction. And it comes out with the value in 2015 of 18.44 6, so I'm going to call that 18.5. So the equation, and I'm going to make notes to the side, has 18.45. The graph has 15. So clearly there's a difference. Now we are asked to compare in relative terms. Relative terms, think relative change. Except we're going to be, since we are comparing two things, not looking at their change, we're actually finding a relative difference. So a reminder about how to find a relative difference. First, we need to know what value is the standard. And we're told right here that we're going to use the graph value of as the standard. So that means we're going to be taking the equation minus the graph divided by the graph. So sort of the math work, I'm going to do is going to be 18.45 minus 15, all divided by 15. And I'm going to turn that into a percent. And granted, whatever you rounded to, your answers might be slightly different than mine. Or if you got a slightly different prediction from the graph, it doesn't mean your prediction's wrong. You might have, at one point when I was just looking at it on paper, I thought it was closer to 14. And now that I drew a line, it looks closer to 15. So, you can sort of, depending, and if I had done this at 14, just to give you a sense, I would get a very different number than when I do it at 15. So your answer might vary slightly from mine, but that's sort of where like the key over here of me saying what the values I used is important. All right, so we end up getting 0.23, which would be 23%. Now, when we do relative differences, we have a sentence because we can't just say increase or decrease. So I would say something like the model's value of sales is 23% and more than the actual value from the graph. So I'd say the model is not awful, but maybe it's an overestimate. So I might then go back to that 2024 value and be like, yeah, it's probably a little high. I don't expect them to be selling quite that much tequila. And hopefully this helps you better understand the two exponential function problems from this practice. The next page, we sort of move back into just finance and savings, and stay tuned for some future videos on those questions.